it's, of course, not a coincidence that my talk comes just after David's talk. We would like to apply a similar philosophy, as David explained, to superconformal field theories in dimension greater than 2. And there's, of course, been an explosion of results about superconformal field theories in higher dimensions in the last several years. Some of these results were originally inspired by string theory, but then they, of course, took a life of their own. And we have learned many new and surprising things about these models. One of the early surprises was that most of them have no obvious or no known semi-classical Lagrangian description. They are isolated superconformal field theories. And there is a variety of techniques to study them. Integrability for some Lagrangian examples, localization, if you have a Lagrangian, of course, the good old Seiberg-Witten theory on Coulomb branch moduli space. And all of them, of course, is very beautiful and very powerful within its limited scope of applicability. But the situation philosophically, according to us, leaves something to be desired. For one thing, many of these techniques do not fully use the power of conformal symmetry. And conformal symmetry is just not like a symmetry like any other. As David just reviewed, you gain whenever the model is conformal in a convergent operator product expansion. And so the whole structure of how you should think about the problem changes quite drastically. And so our prejudice then is that we should attempt to study superconformal field theories using the conformal bootstrap. And thankfully, I don't have to review this in any detail because we just heard from David Simosafin a beautiful review of the state of the art, especially about the numerical approach in any dimension, but the general philosophy will be very much the same. We're going to use the constraints of the general abstract constraints of cotton-symmetric unitarity, and we will think of the abstract operator algebra of the theory with no reference to any semi-classical field theoretic description. So of course, we were much inspired by this beautiful breakthrough in the numerical bootstrap that David reviewed. But as you will see, a consistent portion of our work will be a piece of mathematical physics, where there will be non-numerics, but that will then feed into something very similar to what David described to you. So the kind of questions we would like to address, I think, fall broadly into two categories. On the one hand, of course, we have more constraints from supersymmetry, and we have some sort of a hunch that, for example, for maximally supersymmetric theories in various dimensions, we pretty much know the complete list. If we know, for example, that we think we know from a variety of arguments that the 2-0 theory in 6 dimensions has an AD classification. We also don't expect in 4 dimensions to have any exotic theories with n equal to 4 supersymmetry. And similarly, there is a catalog in 3 dimensions. And so, in some sense, this is a really theoretical question. Can we prove that the list is complete? And in proving it, learn something about how to handle theory space. After all, the classification of superconformal field theories in various dimensions is really a sub-problem of the harder problem of classifying string vacua. And that's particularly the case if I tell you to classify for me 3-dimensional superconformal field theory with n equal to 2 supersymmetry dually correspond to this vast conjectural landscape of ADS4 supersymmetric vacuum. But then, of course, there is a second set of questions. We may be interested in special theories. And we expect the bootstrap to be particularly powerful if I can specify the theory in a sentence, by telling you a very few discrete data. And a case in point that will, in fact, be the focus of my talk is a 6-dimensional 2,0 theory, maximum supersymmetric superconformal field theory in 6 dimensions. It's customary when talking about it to say that the theory is mysterious or elusive. But you see, our prejudice is that if you think of it as a conformal field theory, there's nothing really so mysterious about it. It's just a conformal field theory like any other with an abstract operator algebra, and the program or the bootstrap should teach us something about it. So that's the general outline, but the moment you start thinking more at a more technical level and trying to go through the program that was outlined in the previous talk, you quickly realize that you have an infinite set of constraints for an infinite amount of data, and supersymmetry is just some extra finite set of constraints. It will organize conformal multiplets into super multiplets, each of which contains a finite amount of conformal multiplets. And so it's not at all clear that this small amount of extra constraints will really bring any order in this complicated set of equations. So we would like to address the question in a different way and ask what is a very natural question. The moment you have supersymmetry, we have been spoiled to think that we should be able to get exact results. And so, to the best of my knowledge, the question had never been asked in this form before. And so, if we consider the bootstrap equations in higher dimensions, do they admit some sort of solvable truncation? Can we find a sector of BPS observables that can be exactly determined? And we have found that the answer is indeed yes for large classes of theories. Unfortunately, not for all possible superconformal field theories, but some very interesting ones. So the moment you have at least n equal to 2 supersymmetry in 4 dimensions, and in fact, what will be the focus of my talk, 2,0 theory in 6 dimensions, it turns out that we can carve out a subsector out of the full operator algebra, which is isomorphic to a 2-dimensional chiral algebra, by which I mean the holomorphic sector of a 2D CFT. And I will not talk about this, but there's also something you can do with n equal to 4 in 3 dimensions, but it's much less constraining. It's just a TQFT. And so this provides enough motivation to focus on this large class of theories to explore this piece of mathematical physics. And in a more pedestrian way, the way, in fact, we stumble upon many of these results, if you write down the crossing symmetry constraints for a 4-point function of BPS operators in any of these theories, you quickly realize that the equations split. There's a set of equations that only care about the intermediate BPS operator exchange in the double OP expansion. And those are the ones that we now understand are captured by this solvable set of the 2-dimensional chiral algebra. And then there's the rest. And this set of equations for the BPS operators are eminently tractable because they are meromorphic, as I will explain. And already solving this sector is very non-trivial because it gives us an infinite amount of information about sometimes exotic, semi-short, protected multiplets and their OP coefficients. So this is something that goes beyond spectral data. It also tells us about the interactions. And this can all be done given some very minimum physical input, such as what are the flavored symmetries of the theory and what are anomalies or flavored central charges. So if that's your thing, if you are a mathematical physicist, this is going to be the most exciting part of my talk. But we really regard this as part of a larger program where then this information is fed into the necessarily harder part, which is determining the non-BPS spectrum. And then this provides us a very useful handle on the non-BPS operator. We can input already an infinite amount of protected data. So let me explain the main point of this part 1 of the talk. So we are claiming that in a n equal to 2 in 4 dimensions or in a 2-0 theory in 6 dimensions, we can carve out a meromorphic sector. There's a meromorphic sector of the operator algebra, which really means that I consider a set of local operators which are lying on a plane. So the plane does nothing special happening on this plane. I, by fiat, decide to consider correlators on that plane. There's no surface defect or anything like that. And then these correlation functions are meromorphic, where Z and Z bar parameterize this chiral algebra plane. And the reasoning is familiar in supersymmetry, and we're all accustomed to the idea that if I consider 4-dimensional n equal 1 supersymmetric theory, there's a chiral ring. Chiral operators up to Q exact terms, cohomology classes of chiral operators are, in fact, independent of position. And this is very much the same phenomenon. We consider this subset, which is defined by passing to the cohomology of a certain impotent Q. And the only slightly unusual aspect of it is that it's a linear combination of a Poincare and a conformal supercharge. And then one can show by the usual type of formal arguments that the z-bar dependence is Q-exact, and so cohomology classes are meromorphic. And of course, this is a richer structure in the chiral ring because we still have z-dependence, which gives us something solvable, meromorphic, but still rather non-trivial. Now, because the supercharge is the linear combination of a Poincare and a conformal supercharge, is clear that the cohomology will have to be a little unusual because the conformal supercharge does not commute with translations. So if I consider the cohomology of local operators at the origin of my plane, then they are in the cohomology if and only if they obey a certain chirality condition. Delta is a conformal dimension, L is the angular momentum on the plane, and R is a certain Cartan of the full Art symmetry group. And I will be more specific about it in a second. But you see, this is the kind of chirality condition that we already encounter for ordinary chiral operators. The dimension is proportional to the Art symmetry. Here there's an important distinction. The spin is also involved in saturating the chirality condition. And that's, of course, expected because we have a z-dependence. And so arbitrary a meromorphic derivative will have to leave us in the cohomology. Now, this R quantum number, in the case of n equal to 2 superconformal field theory, is simply the Cartan of the SU2 symmetry. In the case of 6-dimensional theories, we have SO5 Art symmetry. We split the 5 into 3 plus 2, and so this is the natural embedding of SO3 into SO5 that defines this Cartan. Now, as I was mentioning, my funny supercharge does not commute with translations. And if I consider the ordinary L and L bar generators of global conformal symmetry of the plane, which are, of course, embedded in the global conformal symmetry of the 4 or 6-dimensional theory, in our conventions, it turns out that Q commutes with the left-moving generators, but not with the right-moving ones. And so as I translate the operator away from the origin, if the operator is Q close at the origin, it possibly cannot remain Q close away from the origin. And in order to construct operators, non-trivial cohomology classes away from the origin, we need to twist the right-moving SL2 bar generators by a complexification of the SU2 Art symmetry as such. And then one discovers that these twisted Hattie generators are Q-exact. So what this actually means is that we are, as we translate from the origin, we are rotating in SU2 Art symmetry space as we move. And so the SU2R rotation is locked with the Z-bar dependence in such a way that this remains Q close, and then the chirality condition is simply the statement that the right-moving Hattie generator is 0. And then this is a repetition of what I said a couple of slides before. The cohomology class will be independent of Z-bar, and so we have a meromorphic operator product function, which is clearly closed because the operators are all annihilated by Q, and so this is precisely the structure of a two-dimensional chiral algebra. So this was a little bit abstract, so let's practice on an important example. Let's consider the simplest 6-dimensional theory with 2, 0 supersymmetry, which is, of course, the free abelian tensor multiplet. There are 5 scalars, where I is an SO5 vector index of the Art symmetry, some fermions and the self-dual 2 form. But we need only focus on the scalars because a simple calculation will tell you that scalars are the only components that can possibly saturate my chirality condition. And so if I consider the 5 scalars and I split them into 3 plus 2, where 3 is the vector of SO3 inside of SO5, and I consider the highest weight vector of that SO3, that is my chiral operator. It has 0 spin. In 6-dimension scales have dimension 2, and the Art symmetry being this highest weight has weight 1. Then I go through the construction I outlined before. As I move away from the origin, I'm instructed to add Z-bar dependence. So you see, away from the origin, I take a linear combination of the highest weight and of the lower weight components. And in fact, this is necessary to get a non-trivial correlation function because if all the operators were pointing in the same direction in Art symmetry space, the correlation function would vanish by selection rules. And so here are the simplest possible example of how this meromorphic dependence comes about. Obviously, the operator having a non-trivial OP with itself is phi with phi star, for example. And so if I compute the OP of this guy with itself, the only non-trivial component I find, if I put this at the origin, then these terms are gone, only this is left. And so to find something non-trivial, I need to put a conjugate here, but the conjugate comes with a z-bar square. And in 6 dimensions, I have 2 operators of dimension 2, which give me 1 over x to the 4th, and the z-bar dependence cancels out. And in fact, you can quickly show that the whole theory of the free abelian tensor multiple twisted in this fashion is isomorphic to a U1 affine current of central charge 1. Of course, now we want to proceed to interacting theories, and the general outline of our program is always the same. First, exploit symmetries as much as you can. And symmetries here mean representation theory. So we know the representation theory, the 2,0 theory of the superconformal algebra in 6 dimensions, and so we can pass all the various supermultiplets to a sieve that tells us which supermultiplets can possibly have candidates in this cohomology. And we also know that the theory being a conformal field theory will certainly have a stress tensor, and by supersymmetry, there will be a lowest component of the tensor multiple, which is a scalar operator of dimension 4 in the 14th dimension representation of S of I, which is the symmetric spaceless tensor. This operator will generate, by the construction that I outlined above, by going through this twist and this extraction of the cohomology class, a meromorphic spin 2 operator on this chiral algebra plane, which we identify as the stress tensor. And so something rather remarkable happens. You started with a theory that had only guaranteed to be invariant with the global symmetry, and this global symmetry gets universally enhanced to Virasoro symmetry with central charge proportional to the 6-dimensional conformal anomaly because we have normalized the free tensor to 1. You can then study 1/2 BPS multiplets more generally, and they will give additional higher spin generators. And in fact, you can prove a little lemma that if you have a generator of the BPS ring, that necessarily gives you a generator of the chiral algebra, where a generator of the chiral algebra is an operator that cannot be obtained in the non-singular OP of other operators. And then there's a whole zoo of semi-short multiplets that we don't have time to go through, but the story is much richer than just BPS multiplets. After having exploited the general symmetry constraints, we now want to look at specific examples. And of course, here we have a candidate list of theories. So let's start with the simplest one, the 2-0 theory of type A, the theory on N-M5 branes. And here, what do we know about it? Well, we know it's 1/2 BPS ring, because we can identify with the ring of holomorphic functions in the moduli space. And we know, for example, that in the case of the N5 brane theories, the generators of the ring are n-1 operators with this dimension, which are in the trace symmetric representation of S of 5. And by our previous abstract arguments, we get n-1 generators of the chiral algebra, which are in fact of spin 2 to n. And the most economical scenario is that there are no other generators. And in fact, this passes the check that with this assumption, we can reproduce a superconformal index that had been previously computed by Kim, Kim, and Kim. And it's very likely that if you ask what is the chiral algebra with this set of generators, there's a unique way to solve the constant symmetry constraint. This is obvious for if you have a single generator, if you have 2 of them, you have 2 of them, you have 2 and 3. It's the famous original W algebra of Zamolodchikov. And it's believed to be true more generally. And so here's the bootstrap work for you. From a minimal set of assumptions, in this particular protected sector, I carve out the answer. The answer is the WN algebra. And from the matching of the conformal anomaly, I can tell you that this is the value of the 2D anomaly. And more generally, by looking at the chiral ring of 1/2 BPS operators, we can make, of course, a rather obvious leap that for the 2-0 theory of type G, we have the WG algebra with this particular combination of group theory invariants. And this, of course, rings a bell with the AGT correspondence. It's not, of course, coming as a surprise that the 2-0 theory has a WG algebra inside it. But here we have a very microscopic realization of it in terms of correlation function of actual 6-dimensional operators. Now, what can we do with this? So I will show you later what to really do with it, which is rather non-trivial, which is the full-fledged bootstrap. But already at this level, we can make a very interesting prediction. Because since we claim that half BPS operators form, when appropriately twisted, form this non-algebraic system, now for general endpoint function, the relation between this subsector and the full-fledged endpoint function is complicated. You have to do the twist. But for 3-point function, the relation is immediate, because 3-point functions are uniquely fixed once you tell me the conformal dimension and the arc symmetry indices, and all that remains to be fixed is the coefficient. And so I can simply read off the 3-point function by half BPS operator to 0 theory algebraically from the WN algebra. So this gives a first principle calculation of the 3-point function of half BPS operators for finite n. Now, a large n, we need to take a double scaling limit of the algebra. We scale the central charge like 4n cubed, and in the limit, this reduces to a classical Poisson algebra, which is extremely complicated, but fortunately, this gentleman had computed these Poisson brackets, and by some significant amount of messaging, we find that the 3-point function of quote-unquote double single trace operators in this large n limit, in this generalized free field theory limit, take this form. And so this is a completely algebraic calculation which magically matches with the calculation was done maybe 15 years ago holographically using ADS-FT, using the description in ADS7 times S4. So a very non-trivial check of the logic, but in principle, we have the answer at finite n. So in principle, we can compute 1/n corrections, which should tell us about M theory on ADS7 times S4. Now, I don't have time to go through the same story in 4-dimensional equal to 2 theories. The story there is, in some sense, richer, because we get non-unitary chiral algebras with a very interesting representation theory, where the chiral algebra generators encode, in terms of their algebra of nulls, the geometry of the 4-dimensional Higgs branch. This is just meant to be an advertisement for you to look at it if you want. Now let me go back. Now I'm transitioning to part 2 of the talk. So far I told you how to extract certain protected data using this algebraic abstract approach, but now I want to go back to the full-fledged 4-point function. So here's the 4-point function of 4 operators, each of which obeys my chirality condition, but I'm not twisting them. I'm considering the full-fledged dependence in terms of SU2 arc symmetry indices. And of course, this 4-point function gets contribution from both BPS and non-BPS operators. And if I project the operators by doing the twist that I described earlier, this complicated 4-point function collapses to this simple meromorphic correlator, which is computed by the chiral algebra. So that's the relation between the full-fledged 4-point function and the chiral algebra. I need to do a certain projection that extracts this meromorphic piece. Now, if I consider the double OPE expansion of the full thing, there will be a piece that captures the 1/2 BPS operators and a piece that captures the long operators. And the take-home message that the short operators can be completely recovered from knowledge of this meromorphic function. And so this is a double OPE expansion where, like David earlier, I'm expanding in blocks, except that now they are the blocks of the superconformal algebra, which are in fact just the calculable and finite linear combination of the standard bosonic blocks. And so the flow chart for how we set up the problem, you give me some minimal amount of physical input, flavored symmetry of n equal to 2 theory. What are the central charges? That is enough to completely determine the chiral algebra correlator, because it's just a meromorphic set of equations that can be solved in terms of this small amount of data. From there, I can solve completely for the short spectrum and its OPE coefficients. And here there is an important technical assumption that in order to do that, I need to assume that there is no higher spin symmetry, which is a safe assumption, because if I had higher spin symmetry, I would know that the theory contains a free sector, so I'm just synthesizing interacting theories. So that determines the short part, and finally, I'm ready to solve the hard problem for the long part. And in fact, there is an intermediate step here, which is interesting in its own right, since, after all, it is the case that I can completely determine the OP coefficient squared in terms of this minimal amount of data. I can already ask at this step, what are the constraints of unitarity on the theory? And so if I demand that the short OP coefficient square are non-negative, I learned that the central charge of the theory cannot be arbitrary. It must obey some novel unitarity bounds. For example, this is a particularly interesting one. If you consider an n equal to 2 theory in 4 dimensions, which has some flavored symmetry, GF, the C is the conformal anomaly coefficient that features in the Weil square invariant. H is the dual Coxeter number of G, and K is the flavored central charge, which is just a normalization of a two-point function. This inequality must hold true. So for fixed conformal anomaly, K cannot be too small, which, if the theory admits holographic ADS5 dual, is well, I would say the most precise statement so far of the conjecture of gravity as the weakest force. Because you can interpret the left-hand side as giving the Newton constant, the right-hand side as giving the gauge coupling. And so finally, we can write down a sum rule very similar to the one that David had. In fact, this is precisely the one. Oh, no, something. Never mind. It's almost the same as David had, except that he had it on the left-hand side. But that's just a difference of convention. So he had something equal to 0. I'm putting the identical contribution to the right-hand side here. And so we play a very similar game. And the game is that we want to isolate the piece that we know. And here we know a lot more than in the previous talk, because we have resummed the contribution of this infinite set. I absolutely cannot read. 0, OK. Of this infinite set of operators. And so let me simply flash some numerical results. So there are 3 cases that we study. 2, 0, n equals to 4, and n equals to 2. So these are the results for the 2, 0 theory. We can put a bound similar to the one that David had just by studying the universal 4-point function of stress tense. So we find that the leading non-protected scalar has to be smaller than these curves. And within numerical errors, we see that for large central charge, we recover supergravity, because for large central charge, the leading non-protected operator is a double trace operator. With even better accuracy, we can do this in spin 2, and we recover the double trace operator of spin 2, and with even better accuracy from spin 4. And something very interesting is happening for small central charge. This vertical line is the A1 theory. But we believe that with infinite accuracy, these lines will move all the way here. And something interesting is happening for the A1 theory. But already at this stage, we can put rigorous bounds on the non-protected dimensions of the theory for any value of the central charge. This is very much in the same spirit of what we did for n equal to 4 Superyan-Mills, where we were even able not only to show that for large central charge we get double trace operators, but even to match the corrections to the anomalous dimension that come from Witten diagrams in ADS5 times S5. The bootstrap bounds are saturated, including one of our central charge corrections, which is certainly very non-trivial. And so our speculation is that in all of these examples, these curves are to be taken seriously. They're telling us not just about the bound, but they're telling us about the actual value of the leading non-protected dimensions. And finally, this is my last plot, and then I can conclude. At the beginning, I started with 2 questions. One question is, can we study models of particular interest? And I show you here how to study, for example, the 2,0 theory. But the other question was about theory space. So this is the kind of question you can ask. Consider a completely general n equal to 2 theory in 4 dimensions, which with flavored symmetry GF and flavored central charge K. This is an exclusion plot. So the possible theories must lie in this white region, so long as they have SU2 flavored symmetry and n equal to 2 supersymmetry. This is the free hypermultiplet. And you can imagine that with infinite precision, these curves will go all the way here, but then some very interesting feature is going on here. We are not able to rule out theories down here, And so this is very speculative to say, but it's perhaps an indication that there are theories in 4 dimensions which have a central charge smaller than free field theory, which would be some 4D analog of the Ising model. And I think I'm ready to conclude. This is the outlook. I did not talk about class S, and there is an intriguing interplay between some rather striking mathematical physics and hands-on numerics. Thank you.
Time for questions. Ed, please.
We think there should be a precise correspondence, but we have not been able to make that precise enough for me to talk about it in public, but I will be happy to talk about it with you. So the general idea is that we find this chiral symmetry algebra, and now we need to find non-trivial vertex operators that transform under it. And the obvious guess is that those will come from codimension 2 defects in 6 dimensions. So if I consider the 6-dimensional theory, I have this chiral algebra plane where my cohomology lives of local operators, local 1/2 VPS operators. And then I have transverse, I have codimension 2 defects which are localized on the plane. And the guess is that they will transform as non-trivial modules of the algebra. And we are still confused about several details. That's why at the moment it's a suggestion. But yes, we do think that eventually that should provide a microscopic derivation.
If there are no more questions, let's thank Leonardo again for the beautiful talk.